So is everything fine, Gabriela? You can hear me or see me?
Yes, we can hear you. I wanted also to say to everybody that we started recording this webinar. So good
Oh,
morning,
yes.
everyone.
Yes. Hello, everyone. Welcome to our SAM webinar on qualifications for designers in additive manufacturing. We will have really nice presentations from 3 experts of this field. But before that, I want to shortly go on with a presentation about the International Additive Manufacturing Collocation system that the SAM project is trying to build up together with many other EU-funded projects. So, okay. EWF, the European Welding Federation, is the coordinator of the SAM project, and they are trying to build a kind of bridge between the education and training and the industry to set up a standard, unique qualification system for additive manufacturing. So up to now, together with SAM and other projects, the International Additive Manufacturing Qualification System has determined 4 profiles, international metal AM profiles. These are the process engineer, supervisor, operator, and AM designer. And for these 4 profiles, these competences has been, or certifications has been prepared. In the next term, new competence units to build up these certification programs are being worked on, such as electron beam, powder bed fusion, material jetting, binder jetting, and also as well as the polymers and composites in the long run. So regarding the designer profiles in Imqs, there are several projects, as I said, Destin, SAM, Claim, etc., working on preparing the profiles for additive manufacturing qualification systems. So regarding the AM designers, as you can see, designer is determined as an advanced level 6 type of profile, where you can have the certifications for powder bed fusion and direct energy deposition. For the technician, it will be level 4, independent level 4 qualification with PBF and DED. For the AM designers, it's more a kind of full package with design of polymers, processes and mechanical engineering processes, etc. As I said, SAM plays a critical role in establishing the IAMQS. These are the 3 main objectives of the project, that is to analyze present and future AM skill needs, create an observatory, and implement a European AM qualification system. So for reaching to the observatory, you can see the project website, that is skillsforam.eu, where we are trying to map and monitor the entire AM industry, as well as we are trying to follow up the students, trainees and job seekers in additive manufacturing. So we invite you to join some project groups, especially on LinkedIn. We have students, trainings, job seekers in additive manufacturing group on LinkedIn, which has more than 500 participants up to now. The main goal in this group is to follow up the business market, let's say, some posts for some recruitments, etc., some news. So it is an interesting area for especially young people who are seeking some new careers in additive manufacturing. So finally, thank you for joining our webinar. And one last thing important for you is that please take the feedback survey for the event, where my colleague Gabriela will put on the chat screen. That's just a short survey to evaluate our webinars and other activities of SAM. So we will be delighted if you take the survey just for a few minutes. So I'd stop at this moment, and maybe let's say, okay. I should invite our next guest, Ijin Pei, to make the presentation. But firstly, I would like to introduce Ijin to you. Ijin is the Associate Dean of the College for Engineering, Design and Physical Sciences at Brunel University in London, in UK. He is Director of Product Design Engineering and Co-Director of Brunel Digital Manufacturing Center, a hub for engineering, design and manufacturing. He is the chairperson of UK National Standards Committee for AM, that publishes standards for AM. He is also chairperson for International Standardization Committee for Additive Manufacturing Data and Design, ISO TC 261 Working Group 4. He is also a chartered engineer, chartered environmentalist, chartered technological product designer with a strong industrial track record, generating new knowledge and finding solutions with significant impact for the industry. So Asian research focuses on design for AM and 4D printing. So a lot of things that Asian is doing. So thanks to him for joining. Today he will talk about design of additive manufacturing, how it can be applied to product development, and he will introduce a short case study. So Asian, the floor is yours. Thank you.
Thank you very much, Kenan. I'll share my screen shortly.
Yes, of course.
But a very good morning to all of you. And Kenan, thank you so much for inviting me, Kenan, especially from EPAME on behalf of SAME, and also Gabriel from Sasimu. So I'll share my screen. I hope you can see that. So Kenan, if you can confirm that my screen is showing, would be quite helpful.
Yes, we can see it.
Okay, thank you. That's great. So let's have a look at the slides today. So I've prepared a couple of slides. It's just meant to be an overview about design for additive manufacturing. So one part of that would be obviously an introduction to myself, how I came about doing design for additive manufacturing, and some case studies. So here we go for the slides. So just 3 things to share with you, because I know it's going to be a very short presentation for 20 minutes. First thing I'd like to share with you is what made me interested in this field, which hopefully will also inspire you to be interested in design for additive manufacturing, to learn more about designing for additive manufacturing. And we also obviously want to touch about exactly what is design for additive manufacturing, or what is DfAM, how it can be applied to your own industry. For example, for me, from new product development, how I've actually used it, and to show a case study example from a paper, and also to share with you some of the foreseeable challenges about the future of design for additive manufacturing. Kenan, I think there's a hands up, so I'm not sure whether you want to pick that up or maybe later.
It is better you've complete your presentation, although we planned a Q&A at the end of all presentations. Maybe it is better you answer the questions regarding your presentation and we go on. Okay, so dear Fatih, let's Ijin to finish his presentation, and then of course I will take your questions. Thank you.
Brilliant. Thank you. Okay, so just to begin briefly to share with you a little bit of my personal background, I can assure you that the photograph that's being shown in me is the same person. The only difference is obviously I've grown a mustache, but it doesn't give me any extra superpowers. It's the same person. And obviously for me, as what Kenneth mentioned, I work in Brunel University, London, based in the UK. More than welcome to visit us when things get better. We very much appreciate you, having collaborative opportunities. And I've got a research background in design for additive manufacturing, as well as in 4D printing. I will touch very briefly on 4D printing in my last 2 slides for today. And I'm also involved in standards. I think standards are just an excellent example about trying to capture industry best practices. And I'm involved in standards at the international level. So I chair TC 261 Working Group 4, which is the technical committee in ISO level, which develops standards for design in data for additive manufacturing. And also in the UK, I'm also the chair for AMT8, which is the National Committee for Additive Manufacturing. So I've been involved in that because as an academic, I do teach standards, and I'm also involved in the standardization work. I'm also a chartered engineer and a chartered environmentalist, and also a chartered technological product designer. And I also worked for Springer Nature as an editor-in-chief for Progressive Additive Manufacturing Journal. So hopefully it gives you a little bit of background about me and my background, about myself. So the story so far, so I used to obviously teach additive manufacturing, and these are some student projects, which we use these not just as a way for students to be interested in new product development, but also to have the ability to be creative, to use additive manufacturing as a way to realize their creative ideas, to be innovative, right? So in here in this project, which I was module leader back in 2012, so I started doing this back in 2011, 2012, 2013, 2014. At that time, this module was for a master's program about trying to reverse engineer a computer mouse. So they would have to make a consumer product. They would have to work through taking out the electronics and designing a enclosure around it. But all of those buttons, the mechanical features, the click buttons, the scroll wheel, and obviously the optical laser sensor would have to work. Right, so they would have to reverse engineer that, but also ensuring the functionality is still being met. And that was obviously not easy at that time. About 10 years ago, additive manufacturing and the software and the hardware was still quite expensive 10 years ago. So by being able to actually achieve this at that time was really something that was very, very proud of the students to be able to achieve that. This is just some snapshots of that, but you could see some attempts, for example, to have textures along the edges, and you could see that the edges of that, the profile, it's a free-form profile. It's quite difficult to achieve at a point of time where the use of magics or the use of software was still developing. It wasn't very easy at that point of time. You could have an extrusion or you can have an emboss feature, the parting lines, bringing them together. You need to get the right fit and tolerances, or even to get transparent or translucent materials. At that time, 2012, 2011 was not that easy, and to also get the mounting bosses, the snap fits, and that detail, and all of these computer mouse or mice would have to work. If they didn't make it work, they wouldn't get the grade. So very, very impressive to be able to achieve that at that point of time. But that was the beginning for me. But actually, for me, when I got interested in additive manufacturing, when way back in 1997, so back in 1997, was really able to try and work my way around to produce my first 3D prints. But I still have that actually back in 1997, and this was made from the 3D Systems Viper SI2 machine. Some of you might know of that. So it's actually through the vat photopolymerization. And again, you could see back then in 1997, we were already able to achieve parts that would have step feeds. You would have obviously separate pieces. You could get some details in there, or you could get all of those small little details to actually realize a product. But you could see the quality, obviously. The surface finish, the resolution, and discolorization was quite bad. And that was the beginning for me to get into additive manufacturing back in 1997. And for me, obviously, I can say, I've been involved in standardization since 2015. I've been the chair for ISO 661 Working Group 4, and you could see a very good spirit of membership across the world, very international membership. You have people, for example, from different countries, different types of organizations. I'm also involved, obviously, in books. If you're interested, you could just read it and find it out more. So I'm quite conscious of time. I just want to talk to you a little bit more about why design for additive manufacturing and why is it important. And to me, I like to draw attention to sustainability. Obviously, we've had COP26. We know the issues about waste being produced. We know that if you've got a 3D printer running idle, it consumes energy. It's not for free. Your startup time, idle time, and downtime takes up energy. It's a huge energy consuming machine. So is additive manufacturing truly sustainable? If it is, can we make it better? But if it is not, how can we ensure that additive manufacturing can be a green production process? If you're into powder bed fusion, 70% of the material, the powder, can be recycled up to maybe 5-6 times, and then you have to dispose the powder and you need to store it. And there is also a storage shelf life. So if not, how can we ensure that AM is sustainable? And to me, one of the answers to this question, to this holy grail of questions, would be design for additive manufacturing. If we can apply the right techniques right from the beginning of the process in design for additive manufacturing, then maybe we can try to do our part to achieve a much more sustainable society. And obviously for design for additive manufacturing, we know that there will be 4 key points, or maybe even more. And the first thing is to try and take advantage of AM's unique capabilities. By what I mean by that is to ensure that you can actually achieve free-form complex surface through AM, but you can achieve very complicated parts. You don't need multi-part tooling, for example. So you can actually use that to the benefit for batch production, for customization, for personalized products to really take advantage of AM's unique capabilities. And secondly, AM is integrated in the digital process, maybe digital twinning, through CAD tools, topological optimization, generative design, and all of that tools also allow you to capitalize on new design spaces. And AM, design for AM should also be used and considered for the entire process chain, even post-processing, even at the end of the process. And we can also design around manufacturing constraints. So here, design for additive manufacturing to me would be using that to enable shape complexity. You can also use design for AM for functional parts, generative designs, multifunction designs, and we should also not use AM to replace existing manufacturing production methods, but sometimes it could be complementary. Sometimes it could also be used for very unique use cases, for example, for medical devices, or for example, for aerospace parts, and also applying design rules and guidelines. Now, I just want to share with you one example for DfAM, which can be achieved at multiple levels. So designing for additive manufacturing at multiple levels. But let's take a look at that, Kip. So here, this is an example, not my project, but this is an example from a paper which I thought I would like to share with you. So essentially, this is a part which has been used for the aerospace industry as a kind of a testing component for the V22 Osprey. If you're an aerospace freak like me, you know the V22 Osprey is a tilt rotor, a double rotor, what we call sort of a helicopter kind of aircraft that has been designed by and used by the American Army, as well as American US Air Force. But here, this is actually a testing equipment. But you know, in the testing equipment on the left-hand side, you could see that there are so many components that they need to bring together to test the equipment. And as a result, it becomes very complicated to have multiple components being brought together. Every time they want to test it, they have to assemble that and to use it, and it's no longer cost effective. And the way forward is to apply the use of design for additive manufacturing in order to come up with a multi-part component. And as you can see, they have multiple channels that are integrated to be able to fit into the main sensors or to the rest of the hardware. And this part here, which they have designed in order to replace all of these components, has helped to save the weight by 60%, and that's massive. And also to reduce the height by 53% to support shipping, right, and also for storage. And as you can also see, the internal details of the channels here. In the channels, they have also managed to achieve different types of cross-section for the internal channels, which is not going to be achievable by normal means. And as you can see, they've also applied the use of FEA, because as you can see, they have tried to produce that through standard uniform walls, as well as through teardrop shaped walls. And in the teardrop shaped walls, they apply FEA, and you can see some parts which are in weight would have a lot of stress. And you can see in some parts they have tried to thicken it. And by thickening them through variable thicknesses, they have made some parts stronger than usual. Otherwise, obviously, you will not be able to achieve the kind of part integrity. And also, you can see in terms of trying to design the part for post-processing, you need to keep some of the surfaces flat so that it can be clamped onto your bench vise, or to be clamped for CNC machining, or to be clamped so that this part would be the centering, the dead center for you to machine through, to be able to drill that hole through, and to maybe get a screw thread or something like that as a machining guide. So by designing for AM for post-processing, keeping those parts flat, it's easier for you to achieve the post-processing stages. And lastly, you can see also in the last two images in here, they've also included weight saving features, making some parts intentionally hollow. You could see the cross section is actually hollow. It's not a solid part, which saves material, also reduces manufacturing time, and obviously it's much more lightweight. It's not heavy. You can reduce the weight. So by just designing everything in one go, wow, you have actually achieved quite a lot of things through a design problem, you have achieved at least four objectives: to bring together all of those parts through part consolidation, optimizing them in the designing process, thinking about post-processing in the manufacturing stages, and also for transportation, as well as other things saving material through lightweight features by hollowing the parts. And it's just one example of what design for additive manufacturing can really do for you. And what we usually do this, so sometimes in what I do, in what I teach, sometimes we refer to a very excellent reference, which is ISO ASTM 52910 2018 version, which talks about additive manufacturing design requirements, guidelines, and recommendations. Essentially, this is a flow chart to explain to companies, users, or people interested for design for additive manufacturing, yes/no diagram, what you need to think about if you plan to apply design for additive manufacturing. And this is a very simple flow chart that tells you how additive manufacturing can be beneficial. I won't go through that in details, but you could see, for example, in here, in the center part in here, you could see that this flow chart enables you to think about many things fast forward. For example, thinking about the potential for customization, personalization of parts, thinking about the potential for lightweight saving features, thinking about the potential for internal cooling channels or structures or honeycomb channels, or even lattices, thinking about trying to integrate functionality into those parts. Maybe you have ball bearing features, you have moving assemblies, and things like that, functional features that would not be available through conventional manufacturing. Thinking about designing for surface structures, for example, for medical devices, you want to have rough or even smooth surfaces. And lastly, sometimes even think about material options to have combination of different materials or even hybrid materials, blended materials, non-homogeneous materials. Think about those opportunities for you for when in the design for additive manufacturing stage. Okay, move on to the next slide. So just a couple more slides for me. I'm quite mindful of time. So also in design for additive manufacturing, we also think about some of those what we call fundamental design rules. These fundamental design rules are usually set because of the laws of physics. For example, we know that you will need support structures if you have any overhangs. And what we mean by overhangs would be parts that seem to be on top of each other. They have an overhanging surface which pull itself down due to gravity. So you need a support structure in the build process. But we know that parts with an angle between 30 and 45 degrees could be at risk. Any parts lower than 30 degrees will definitely need a support structure. And those parts that are more than 45 degrees very rarely need support structure. So you could see, for example, in this design in here, one without support structures and the second one with a support structure, also without support structures as well. You can achieve that through the use of fillets. By having fillets, you will not need a support structure in the build process. Whereas if you don't have a fillet, then it's quite likely you will need a support structure. And having support structures means you probably waste a lot of time by trimming that off, grinding and polishing that off. So you could make your life easier by trying to understand how the part geometry, in particular the angles, may require you to include support structures or may not require you to include support structures. And likewise, also some of those design rules in terms of the wall thicknesses, thinking about different types of material processes, AM processes, the materials being used, may need to think about the minimum wall thicknesses, the size of your machine. You may need to think about maximum part size. If a machine only has that size, then you may need to think about splitting the parts up or reorientating that to the z-axis instead on the y or z-axis because of the maximum part size you can build in a machine. Or thinking about tolerances and fits for additive manufacturing, you need to think about part shrinkage because of the thermal expansion. You also need to think about the minimum hole feature that the resolution of your machine can actually print. These are just some examples about designing for additive manufacturing in terms of the fundamental design rules. I don't have time to go into everything in detail, quite mindful of time. So moving on to my last couple of slides, as just a quick introduction. So where does the future hold? We know that there's a huge potential. If you're designing it correct, we can potentially play our part for a much more sustainable society. But there are some future challenges ahead. And one of the future challenges that I would foresee would be about 4D printing. Some of you might have heard of that, but some of you might not have heard of that, but it's a growing field. And I did a search back in Scopus in Web of Science, and you could see here in Web of Science, there's a growing trajectory in terms of the numbers of papers. So many papers, even the histogram cannot keep up with that. It's growing up exponentially in terms of the number of papers or citations being produced for 4D printing. And you can see that because it's growing, there are also a lot of books being published in terms of 4D printing of soft materials, 4D printing applications, and things like that. So one of the grand challenges that we face would be about design for 4D printing. And we can see also that design for 4D printing would lead to a lot of applications. And these applications will need us to create new guidelines for designing for 4D printing. So no longer design for additive manufacturing, but designing for 4D printing. And here it also shows, and from this diagram, which has been adapted from Fahang's work, we can see that there are a lot of other elements in terms of designing for 4D printing. You need to think about AM process, the external environmental stimuli, the type of materials that you use, the CAD and mathematical modeling, the interaction mechanism, and also design is being key for 4D printing, because you need to think about the shape changing behavior, as what you can see in the diagram below, that the design of the CAD model, the geometry, and how we overlay the materials on top of each other will influence shape changing behavior. The time of sequence, the shape of change, speed of change will be affected through this. Okay, so that's it for me. I hope I've not taken up too much of time today. I know I've exceeded my time a little bit, but thank you very much once again for this opportunity. Happy to entertain any questions.
Yeah, thank you, Eugene. That was fast and compact. Thank you for the presentation. I think we had one raised hand from Fatih Patır in the beginning. So Fatih, if you want to ask your question now, maybe it's a time.
Thank you, Kenan. Actually, thank you for presentation. Actually, my question was already in the presentation, so I don't have a question at the moment. Thank you again.
Okay, you're welcome. So next question is from Jonathan. So Jonathan.
Hello, good morning. Thank you, Eugene. That was really interesting. I'm wondering, as part of your teaching, do you incorporate any information about, the rules that determine the cost of AM? Because, my background, I come from an AM bureau environment, and the problem that the manufacturers face is that people are producing beautiful, wonderful, clever, exciting objects, but unfortunately they're not worth making. They're too expensive, and that's where it all falls apart. You have to design something that you, as you're designing it, you're confident that it will be valuable enough to produce in the end. Otherwise, you're wasting your time. Just because you can make it doesn't mean it's worth making. And I think that's something that's really important to be built into the education of AM.
Thank you, John. Thank you, Jonathan. I completely agree that I think thinking about cost is just one of the key elements, not just for businesses, but also for students, because additive manufacturing can be obviously a very expensive resource in terms of not just the materials, the machine, but also the labor and expertise and things like that. So, but returning back to our question, cost, it would say it's only very lightly touched on for students, what we call projects. It's not merely touched on, but I know that for other universities, I can be honest with you, that there are some universities for the master's program, they do actually include course as one of the key modules or key subjects in there. I know, understand that, for example, University of Nottingham, I've got a couple of friends in there, they actually specialize in the business aspects of additive manufacturing, that what we call the economics of additive manufacturing. Is it worthwhile using additive manufacturing as opposed to other types of conventional manufacturing process, or which type of additive manufacturing process of the 7 AM processes, which will be the most cost effective if you want to produce that aerospace part? Should you use powder bed fusion or should you use DD? And also at different stages, which AM process will you use? And also about batch production. So cost is an important aspect that I think needs to be researched a lot more. But returning back to our question, I personally only lightly touch on cost, not a lot, but I do respect that it's a hugely important topic that could become an overlap between business and economics as well as design. There should be something in place. Maybe in the future, there could be a talk, a webinar, precisely in this topic, Jonathan.
Yeah. Okay. Thank you very much. Thanks.
Thank you, John. Good to see you here.
Okay, are there any more questions? If not, I want to go on with our second speaker. That's Mika Salmi. Thank you, Eugene, by the way. Once again, we'll come back to you at the end of the session with some questions, maybe. Okay, good. Or discussions. So here's our next speaker. This is Mika Salmi from Finland. Mika works as a research director at Alta University Digital Design Laboratory, and he's a staff scientist at the Department of Mechanical Engineering. He made his PhD in 2013, focusing on medical applications of AM in surgery and dental care. He has published more than 50 scientific and technical papers from industrial and medical applications of AM. Currently, he is involved in projects relating to 3D printing of spare parts and medical applications, 4D printing, and researching industrial applications of AM. So today he will talk about different workflows for designing medical and industrial components. And of course, he will give us some good examples in that scope. So hello, Mika. The floor is yours.
Thank you, Kenan. And first, thank you for the invitation.
You're welcome.
And kind introduction. So then I can start sharing, and let's get to the presentation. Okay, I believe you can see the
yes,
slides.
We can see your presentation now. The floor is yours. Okay.
Okay, thank you. So I was planning to talk a little bit about different workflows related when you are designing industrial or medical components, and basically what complexity is related to that. And as said, I work as a research director in Alta University Digital Design Laboratory, and also I'm the president of Finnish Rapid Prototyping Association. So shortly about the content, let's look first where I come from, then why this design is important. Eugene already said something about that. Then a little bit about the personalization and data capturing methods, designing of spare parts, and when the data is limited, what would be the starting point, methods for topology optimized sand castings, shortly about the open source movement, then AM process simulation, and a little bit about future challenges and conclusion. So first, if you look about the additive manufacturing research at Alta, so we have done that since 92. Currently, there is about 15 researchers with the cumulative more than 100 years of AM experiences. We have all 7 ISO AMs, the standard process class in-house, more than 30 different 3D printers. And the group is led by Professor Jouni Partanen, who has worked 12 years in the 3D systems and has more than 50 patents in this area. And what we do? Basically, we look, okay, maybe there is some kind of application. If it's a medical application, maybe some kind of new products or services based on the AM or example, digital spare parts or end-use parts. But of course, then you need the material. You need to think about the quality. Maybe you want to use some new material because that might open up new applications. But of course, then you need the technology also. You need to do the post-processing. Maybe you need to combine different technologies. And also this design is very important because that can be used to optimize to get the better performance. And basically, if you think about the design, so basically additive manufacturing always requires the 3D model. And basically the design is the key to utilize the potential of AM. So there we can optimize, we can make lightweight structures and so on. Also, if you think about the personal product, so where every product has a different design. But also this design includes also the simulation, maybe the AM or the product, and that often takes some design as an input and then gives some outputs. And of course, this simulation you can use to improve the design and iterate. First, let's look a little bit about the personalization and data capturing methods. So basically, let's start from the medical imaging. So there are X-ray based like computed tomography, which can be used to capture patient data, or you use magnetic resonance imaging, 3D ultrasound, nuclear imaging. Basically, with those you can see inside the body, and that usually provides images in the DICOM format. But then you can use the segmentation methods to calculate 3D geometry out of that. So basically, with that you can see inside of the body or a part, and also this computed tomography is used in the industrial settings also. But then there are like different 3D scanning and measuring methods, photogrammetry, light-based scanning, structured light, and so on. So with this you can see external surfaces. And usually this provides the 3D surface data in the triangulated format. And 3D printing requires a closed surface. This is a case study example of like error sources for the medical implants, which includes the imaging phase with the computed tomography, then this segmentation and errors related to that, 3D modeling, then AM, and then if you think about that, there is this thresholding boundary 2 times. And then if you look about where are the biggest errors, they are mostly related to this additive manufacturing part, so the actual manufacturing, and also this thresholding. Actually, the imaging error and 3D modeling error are much more lower than the others. So basically, and then the design error can be very close to 0 because it's a digital way. Then little bit think about what if we need to design spare parts, and maybe we don't have all the data available. So maybe we have the 3D paper drawing. So yes, that's good. So we can scan it. We can make some vectorial files out of it and then use 3D modeling methods, or directly we just read the drawing and 3D model it again. And also we can do that from the digital 2D drawing. We can import that directly to some CAD and but of course that would require some modeling work. Or then we have only the physical part left. We have maybe the last spare, or we have the broken part. So we can do traditional measurements and then 3D model it. Or we can 3D scan it and then use that for the 3D modeling. Or we have the 3D model already, so we can use this for the production. Or then we can use combined. Actually, like if you have a 3D model and 2D drawings, because the 3D model doesn't have the tolerances usually. So that would be actually maybe one of the best. And then we can also see what was the manufacturing methods and so on. Because it's like it's just not enough if we have only the geometry, but we need the tolerances and material information, or we need to be able to estimate what we want to do. And then let's quickly look about the topology optimized sand castings. So basically you can 3D print sand molds, and this is a case study about like this is a suspension linkage from a Formula student car, which has a basic design which was optimized as lightweight as possible for the normal casting process. But then, okay, maybe we can make a topology optimization. We get the raw results, and then we get this. We can smooth that or redraw the component. Then we can use the 3D printing to make the sand molds, design the molds, and then do casting simulations, and based on that, see how the mold design will work. So basically, this part was original from the aluminum alloy, And it was easily made with the basic sand molding patterns. And then when we simulate with the same loads, we can get the raw data out of that. Okay, so it's the raw data looks like that. And how basically we do optimization for this? We have the design space. So we have a where there can be material and what can be changed. So those gray areas are connection points which we cannot change. And then because there is like other parts around it, we cannot grow it too much in any other direction also. Then we have the load and boundary conditions. And then of course we are thinking that this is symmetric using the shape control that helps the calculations. And then we can get the optimized shape. So basically this is raw data, and we can get that to CAD and do casting simulation, and then we can also redesign the component totally if we want. So we made all of these versions of the original optimized and this redesigned one. And also before the casting and before ordering this molds, we did like a casting simulation. So how well the mold feel and will there be some problematic areas there, and where to put the vents and so on. And also same for the cooling. So how it will cool and what might happen there, and is there some problematic areas. And then when we have those ready, so basically we can affect those with the mold design. So if there is a problematic areas, so then we have the mold design ready. We can 3D print those molds, and then we can cast those parts. Then a little bit if you think about like open source movements and how that's related to the design. So first I would like to shortly say about like IPR related. So basically there are maybe closest ones to this 3D models and 3D printing are like example copyright, which protects like original and creative objects, but it doesn't protect any specific materials used for the productions and so on. Or then we have the design rights, like the external shape and features of the whole part or the product, but it doesn't protect raw materials, internal parts, and so on. And then we have the patent right, like innovation and technology contained in an object. And basically a CAD file that contains a plan for a patented item, certainly if it's cited in the patent claims, but it doesn't protect the aesthetic layout. So that's like a very short overview about the IPR related to 3D printing. And then we can think about the open source. I think this COVID-19 was a very good example of this open source movement and its potential. So basically there was a lot of different kind of innovations related to how to help in the COVID. Example, nasal swab for taking samples for testing, face mask, different holder for face shields, and even venturi valves. And actually those were all like open source and shared freely with the different kind of open source or with the different kind of free licenses for emergency use. And that actually shows like this kind of like a cumulative design or cumulative learnings, and then people use those other design to improve designs. Of course, that leads that then there is a many designs of the same object, and you don't know actually what you should use, but still it like it shows how this crowdsourcing might work. And then of course then if we jump to the AM process, if we take example powder bed fusion for metals, it causes distortion and stresses, but of course you can simulate those. Usually you do that with the software, which is calibrated with one material and machine and parameter sets, because those all affect that, which machine, which material, which parameters. So you need to make a calibration run. Then, of course, design the geometry, orientation, and designing the support effect. Basically, when you remove the parts, heat treatments, and so on, those can be taken into account. And that leads that maybe you need to redesign some features. And in some simulations, they allow different 3D forms in opposite direction. So when you print it, then it should be straight. Of course, that leads that you are actually printing a different geometry that you were designing, because you have like a predeform it. And of course, if you have very complex, it might need integration or even the 3D printing tryouts. So with the simulation, you can try to get rid of the tryouts and try to control the deformations more better. And then if you think about the future challenges, so like the new technologies will develop. Example, automation, different monitoring systems, predictive analysis, and so on. And also AI will be there, big data mining, machine learning, and basically you have a huge amount of data set. If you take example modern powder bed fusion metal printing, which has all the monitoring that is available, it will create a huge amount of data. It will monitor the powder bed with the photographs. It might have like a different optical tracking, checking the laser, different so-called optical tomography, melt pool monitoring, and so on. So it can create a huge amount of data, and then you need to know what to do with that. Also, there is a greater use for this kind of topology optimization, generative design, lattices, voxel-based modeling. And then also, as Eugen said, we need to think about the sustainability and the green design. We need to optimize the materials, energy, and so on. And also that leads that we need to educate and we need to reskill the workforce. And then conclusion, there was a good comment about the cost. Basically you need to, I said that you need to look the whole cost and especially added value. If there is no added value, what's the point of making something with the 3D printing or start designing that? So where will be the added value? That's something that you need to think about. And also look the cost, not only the manufacturing cost, look the cost from the whole life cycle of the product. And the design is the key to use the potential. Then this responsiveness, open source movement, COVID is a good example of that. Possibilities in different areas, spare parts, one problem where to get the data, lightweight structures, how to optimize, key performance components. Example, if you can save fuel, it might cost double the component. It doesn't matter so much there anymore. If it's so much, if it's having a much better performance. And then one important aspect related to design, it's like this, there can be different 3D models and modification during the process. And actually then this documentation should be in the up to date and very good, well done. Otherwise it might be hard to go back. Because if you have the original design, then you have simulated that, then you have the little bit optimized design, then you process simulate that, deform it, pre-deform it, then you have that geometry, and then you make the actual part and it has some geometry. So you need to try to think how to document that all. So now questions, comments, welcome.
Thank you, Mika, for your nice presentation. I would like to ask our participants if they have any questions to Mika. I have something in my mind regarding the medical applications. Just want to be sure that you are an expert. What I feel is the correct thing. You know the TRL levels, the technological readiness levels, when we evaluate additive manufacturing among different sectors, what we see is that the medical industry is the highest TRL level industry that's using almost everything from additive manufacturing. So what is the reason of this? What do you think? Because in automotive still it is impossible to apply additive manufacturing in many cases because serial production costs are still too high for AM. But maybe in medical applications it's rather custom made or tailor made. But in general, what's your feeling that why additive manufacturing has been really booming in medical industry?
Yeah, one thing is that this personalization, because if you look the actual applications, almost all of those are like some kind of personal solutions. And then other thing is that in the medical field and basically in the insurance, they have already think about the cost. If the operation cost a little bit more, it doesn't matter if the results are better. So they are actually quite good of trying to look the whole cost cycle, and like what some treatments can cost, but what it might save in some end. So I think they can look a little bit better in that. Then if you think about example this car automotive, they are like it's like a mass customized, but still it's like they make a lot of similar things. They are not totally personalized. So then 3D printing might be a little bit harder there to implement.
Yeah.
And also like the price, of course, the price can be higher, but in the medical usually everything costs a lot.
Yeah.
So
That's
that might help like so-called business case there.
Yeah. You're right. Okay. So thank you very much. If there aren't any other questions apart from me, I would like to give the floor to our next speaker. So thank you, Mika. So maybe
Thank
at the end we have a short roundtable discussion together with some questions and ideas. So thank you once again.
Thank you.
Okay. So our third and last speaker is Roger Barnett from ANSYS, UK. Roger holds a PhD in material science and metallurgy from the University of Cambridge in UK. He has been working in materials industry for the past 13 years in technical research, product management, and marketing. He's an experienced project or product manager, engineer, and metallurgist, specializing in microscopy, high temperature corrosion, nickel alloys, and protective coatings. Recent work has included multi-partner research into heat valorization, implementation of metals microscopy strategy, and engineering software product development. Roger is a senior product manager at ANSYS from ANSYS Granta Selector and ANSYS Granta Materials Data. So his presentation in his talk, he will cover the importance of materials data and data management in additive manufacturing, including a short case study in using collected materials data to select the best materials, process, and machine setup. So before giving the floor to you, Roger, there's a short reminder for our attendees in the chat. I want to repeat again, we have a feedback survey. We will be happy if you take the feedback survey to evaluate our webinar. Plus, there you will see the links for the social media sites for the project, where you can see the website, the LinkedIn pages, etc., to follow the SAM project. So that's all from my side. I would like to give the floor to Roger for his presentation. Hello, Roger. And you already shared your screen, the presentation. It's all good. So the floor is yours.
Thank you. Can you just confirm you can hear me okay?
Yes, we can hear you. We can see you. We see the presentation. Everything's perfect. Please go on.
Great. In which case, I'll crack on. As I said, thank you very much for this invitation. It's really good to come along, both again from EPMA and Sesimo. My presentation is going to be on additive manufacturing and materials intelligence and the necessities and using data in order to improve additive manufacturing processes. Keenan has already well introduced me, so I will skip over this. But I'd like to talk to you about the materials that go into additive manufacturing. So firstly, taking a step back from the details of the additive manufacturing process and look at the materials themselves. and how selecting the right material, the right feedstock, is absolutely critical for making the best additive manufactured products. So it could be done on a cost basis. So are you wasting your engineers' time by doing unreliable simulations? Can you locate equivalent grades if you're manufacturing the same product in different countries, or just use a lower cost material? It also may be you're making something new, a new product, and want to innovate with new materials, or lightweight your product by additive manufacturing or by changing your feedstock. And of course, looking at the environmental footprint of your product and mitigating the risk as well. Is your material strong enough? Is it strong enough when manufactured under certain conditions? Do you have validated design data? And of course, are there any restricted substances in your product, particularly important for anything with polymers? And more fundamentally, how do you optimize a product in the first place? And our previous two speakers have actually touched on this to some extent. It comes in two parts. Firstly, optimizing the design of the product. So factors like the geometry of your product, the loading on it, the thermal electrical performance, the boundary conditions, and so forth. But that's not all. So you can come up with an absolutely brilliant design for your additive manufactured product, and that is really key to optimizing it. But it's only one part of the story. You also need to optimize the materials that go into it from a number of different perspectives. So the technical performance of the materials in this instance, economic. If your part isn't going to be economic to produce, then it's only ever going to be a one-off or a prototype. And of course, the environmental impact and sustainability of both your process and your finished part. So this is becoming increasingly important. And of course, the manufacturing process and the conditions. Combining them all together, both the optimal material and the optimal design, leads to an optimal product. Great. The philosophy is there, but how do you actually do that? So again, I'm not going to advertise that to you, but essentially, materials intelligence and simulation have to be throughout the entire process to ensure your best additive manufacturing practice and your top products. And it's really easy to jump into the fine details of the manufacturing process, your fine design, but there's a lot of industrial development needed beforehand to go from your prototype stage to a routinely produced part. So you need to have the right data to design for AM in the first place to get the most efficient structures you can. You need to be able to set up your build correctly, simulate your build process, and of course, analyze your completed structures and assess your your parts both non-destructively and destructively. Once you've done all of that, you need to ensure that all of the data you've gathered is consolidated, that it's searchable and it's available. One of the biggest problems we've observed in industry is unnecessary duplication of information and tests. So you may have the same organization manufacturing the same additively manufactured part in three locations, testing it in different ways and duplicating what's been done previously. Yes, it's extremely important to repeat tests and see how they vary, but if you're just doing exactly the same tests over and over again that has been done elsewhere or 6 months ago, that is a very large waste of time and resources. And so the main challenges we've observed, certainly for materials data and additive manufacturing, is that the materials data is not captured or tracked across the end-to-end process. So you tend to get poor repetition of AM builds and material testing to recreate this data. Furthermore, on an industrial scale, the relationship between the process and the properties is not always understood. And this is often that there's a lack of detailed understanding of the additive manufacturing process within the organization. And yes, you may have all your extensive material test data, but it's not being used in design and simulation. So this means that your parts need to have much more physical testing, much more non-destructive testing for qualification. Whereas with the right simulation and the right simulation data, you can eliminate at least some of the early stage testing and quickly rule out designs that are unsuitable. So you get a much larger development cost and of course a longer time to market. So just to give an example, this is the sort of data that you might need to manage for additive manufacturing production testing. So looking at the powder, the raw material, the process parameters for the build, the post-machine log files, the heat treatment data, NDT inspection data, mechanical testing results. And all of these need to feed in to one materials management system. So this is just for one sort of standard routinely produced part, and all of these items need to be captured and assessed so that you can go back and understand how a particular aspect of your process is affecting things. So I'll give you one very simple example. We have a part, we have a feedstock, we have a manufacturing process. These are all sorted, they're set up. We have our powder specification. It comes from our supplier. We know the chemistry of it. We know the assessment. We have our property. We manufacture our parts with virgin powder. Comes out great. You know, we have our required tensile strength and we have our required fracture toughness. But by the third reuse of the powder, the part chemistry has not changed significantly. The tensile strength is still fine, but we lose the fracture toughness. And it's only by having all of the data available and being able to assess it in one place and see the patterns that we can start to understand this. So for this particular instance, yes, we know it's fine to make with virgin powder. We know it's fine to make on one or two reuses. But the third reuse, we know that the properties are going to degrade. And we also know that we can't skip the fracture toughness testing, because a pure routine tensile test is not enough to tell us if there is a problem. So it doesn't just tell us how we're doing, it tells us where we need to look in order to do quality control and what we're missing. So example we give, again, I'm not going to advertise at you, like using something like our Grantor MI system for additive manufacturing. So taking information on design, build simulation, part validation, additive build preparation, your log files, your processing, your test data, and putting it all in one place means that you can have traceability and capture of the AM data. And if you put it in a consistent database schema, then it's comparable. You can easily compare test from one area, test to another, and it makes analytics much more straightforward, both sort of in-house and third party. And you can also then start integrating your additive manufactured data with your CAD, CAE and simulation systems. So taking your destructive and non-destructive test results and feeding those in to simulations. You can also, if you have a large enough library of data, you can use it for prediction and making decisions. So the example I give again is Grantor Selector. It's another one of our products. And this has an encyclopedia of pre-collected data, both on conventional materials and additive manufactured materials, with sort of visualization, filtering, solving, estimation tools that lets you start making the decisions about the materials you want to use. And it's not, and the other thing I would emphasize, it's not just about the additive manufactured data. So again, if you have data on your additive manufactured components and also reference data from industry, this is brilliant. You can start using this to make decisions, but often that may not be enough in and of itself. You may need data on the corresponding conventional materials that are in contact with these. You may need to be able to do a comparison, or the properties may simply not be available for your desired feedstock. So taking an example, you may have a titanium 6,4 feedstock, and this feedstock works fine, but you don't have full properties for this particular feedstock, but you do have properties for the parent material. So you can start using that as a reference point and a comparison. So what I'm going to do is probably best show you the importance of additive manufactured data and data management with a case study. So we're looking at a typical company case study in which we're looking at an impeller for a water pump. So this particular impeller is an existing product already, and we're looking, based on our additive manufacturing expertise elsewhere in the company, to start making this in using additive manufacturing as well, both to save on machining costs and on material costs. We know that our current material, an ASI 420 steel, works absolutely fine. There is nothing wrong with that material. You know, we could keep using that endlessly and it would be fine. But we think that it would be better if we can make it using additive manufacturing. So we know that there are certain requirements that this material must have. It must be able to resist centrifugal loading, must have a certain minimum tensile strength and a certain minimum elongation at break. Because of the environment it's going to be used in, it must be resistant to fresh water and wear. And from a manufacturing perspective, whatever machine setup we use to make it has to be able to make a component of the size 250 by 250 by 150. So we've taken some fairly high level requirements and used those to try and select the material to make this for additive manufacturing. So what's the best material? How does it perform against a conventional material? Which process should we use to make this? Which grade should we use to make this? And which machine should we use to make this? Can we do it with one of our existing ones, or are we going to have to invest in something new and different? So I'll show you a short video just running through this case study. Again, it's quite a high level, quite a high level bit of information. Hopefully it should play okay. Yes, it does. Great. So
yes, I think it started, Roger. Yeah, it started. Yeah.
Yep. So we have our product case study. These are our requirements that I've just gone through. And I'm doing this in Selector using reference data rather than user's own data. So showing the sort of data that you sort of have and need available in this, I'll use our Senvol database. So information on a number of additive manufactured parts and their properties. So starting with sort of our material, let's look at, say, a fairly typical nickel alloy, 625, well-known, high-performance, corrosion-resistant alloy, with the sort of information on this manufactured in certain properties. So when this feedstock was made, when you've manufactured using a certain process, what are the mechanical properties that you'd expect, and how does this relate to the feedstock and the machine that was used to make it? So that, very high level information to sort of help you do these selections. But that's not always enough. So going back and looking at materials now, so looking at the material that was used to make this, what its capabilities are, build envelope, volume, even things like floor space and electrical current that's required for it, and materials that are compatible with it. So we're starting to get the sort of information we need. So let's now look at selecting an appropriate material. We've chosen our 420 as a reference material, and we're going to look at what materials might be suitable for replacement. We'll look at the performance index for this particular situation. We have a rotating blade, and we're looking for a material we can optimize against fast fracture and a material that was also optimal against centrifugal loading. We're not just looking at one property of the material, we're looking at a combination of the properties in order to see what's best. All the materials on the top right have high resistance to both fast fracture and centrifugal loading. But that's not enough. We know that there's certain minimum requirements to put in there, both in terms of tensile strength, elongation, and environmental durability and wear. So we use these to eliminate a whole bunch of unsuitable candidates. Go back to our graph. You can see we're now down to relatively few materials out of the thousands originally there. And that's our reference material. There are better ones available, and they're all towards the top right. Great, we found some reference materials. Now we need to make sure that whatever we choose has a corresponding additive manufactured feedstock available. So we set this requirement to narrow it further and say, of the conventional materials, which one have an additive manufactured feedstock? So you can see here, it narrows it down further. 17.4 pH stainless steel looks like our good compromise candidate. So now let's actually look at additive manufacturing data specifically. So we'll plot the ultimate tensile strength and the elongation of break of our components. We'll say only for components made from this particular stainless steel. And you can see here that we have a number of different options available and different feedstocks to help us pick the right one. Great. That, however, is good. Now we can see, right, most of these were made using powder bed fusion. So we have a preliminary process selected. Now look at the material, look at machines available, particularly the making sure we fit the XYZ size of the component, that it supports this particular process, and also that it supports this particular feedstock. So again, I've skimmed through this quite quickly because we have a quite short presentation, and making sure to pick things that are compatible. And from that, we've narrowed it down to 5 candidate machines, all of which are compatible with this feedstock, have the appropriate build envelope volume, and we can carry out a quick and straightforward comparison on them. So just by going through with some quite high level data, some early steps, we're able to identify a good candidate material to make this from. We've identified the technology and the process to make it from, specific feedstock, and also a potential machine to use to manufacture this. And if this particular one is not available, or it's not something that would meet our other requirements, we can look at equivalents and similar ones. So it just shows that once you've built up and you have that data available, the sort of analyses you can do and save yourself, it's the old saying, a couple of months in the library can save you a couple of years in development. So by doing your data assessment and building up your data, having it all in one place and being able to assess it much more easily means that you can save so much time in development, in manufacturing, in finding issues with your product. All of it is about having and managing the data effectively and assessing it. I mean, it's used, the example I give is EWI. They use AM data management very, very importantly. They've transitioned from Excel data sheets to a much more in-depth database handling schema to capture all of their additive manufacturing data, particularly for the America Makes program, and it supports powder characterization data capture from a whole load of AM systems, both sort of destructive and non-destructive testing. And putting this all together gives you an incredible power to assess and understand your products. So I realize that's quite a fast tour through data management and additive manufacturing data, as we only have a short time. But again, thank you very much for listening. And if you have any questions, I will very happily take them at this point.
Thank you, Roger. It was a nice presentation about ANSYS. Being a beginner level user of ANSYS software, yeah, it's really detailed and a software covering many aspects. Maybe just then, as this is just a beginning as far as I understand. What I remember is there are a lot of videos and informative things about ANSYS and the software. You can find on YouTube, etc. That's what I know. Actually, I watched some of these that are published by ANSYS to get familiar with the software. So regarding additive manufacturing, thanks to team of ANSYS doing great work. So it is nice to hear all these aspects of design from the source, let's say. So thank you, Roger, for that. If there are any questions to Roger, I would welcome that regarding design, additive manufacturing, softwares. Yeah, yes, there is Fatih. Hello, Fatih. You can ask your question. Please go on.
Hi, Roger. Thank you for your presentation. Actually, I want to ask you how we can enter the database of this and how we can be part of this partnership in the ANSYS systems. We have a machine producer company and we want to join with the different Anavision machines can be entered this database, I hope. So how we can start for that one? Another question, from another question also, the second one. You are recommend some by looking the experimental data coming from the producer companies or some of the users that use some different kind of machines. So do you use as build product database or do you use the after heat treatment database information to be able to recommend the best machine or best powder type?
Right. Okay. I'll first question in regards to sort of putting, if I understand you correctly, you're talking about putting your own sort of data into ANSYS products, sort of like on powders or parts and so forth. That's something that we look at on a case-by-case basis. So probably best, my email is on the screen. If you drop me an email, then we probably discuss that offline about how we'd handle that best. In terms of the second one about heat treatment versus non-heat treatment, the reference, if it's user's own data, then it can be either. You can look at it in both conditions, reference heat treated or non-heat treated, and you can also log and monitor how the heat treatment affects things as well. If in terms of the reference data, specifically the set I was looking at, yes, it does take into account the effect of heat treatment, but this is a third-party data set that we're using, so it's going to be whether the tests have been done in that particular heat treatment condition. So you can look at post-processed versus not post-processed, but the number of different post-processing steps available as data is going to vary very much depending on your material in question.
Okay, thank you.
Yeah, thank you. Any other questions? So for the last time, I would like to ask you to take the survey. I'm sorry, that's the rule of the European funded projects. In the chat screen, you will find the link once again for joining, taking the feedback survey. Before closing, maybe we can take a group photo. If you can turn on your cameras, all everyone. I will go to together mode, and we will have a kind of group picture. So if everyone can turn on the, yeah, okay. Yeah, it's nice. We see a lot of people here. Good. So is this it? So Gabriela, you are the owner of the event. Maybe you can take a large gallery mode, but at least I will take a picture as if we were in a kind of amphi or so. So let me do it. Yeah, has cheese. I'm taking a picture now. Yes, I did it. Thank you very much. So that's the end of our webinar. Thanks for listening. Thanks for joining. There were really nice presentations from our speakers. So therefore, I would like to thank all our 3 speakers for their great contributions to the webinar. Our next webinar about SAM will be on 16th of December. It will be soon announced on LinkedIn and by mailing. It will be about materials and case studies, a kind of general discussion platform organized by EPMA with the scope of the SAM project. So until then, thank you very much again for joining. Have a great day and hope to see you soon. Bye-bye.
Thank you. Thank you very much, everyone.
Thank you.
Thank you. Goodbye.